Welcome dear students. We are in the series of quantum technology. In this series we are discussing the quantum sensing. Up to now we have discussed the many quantum sensors, in which one of the important is the atomic clock. Last time we have discussed the atomic clock. Now in this series now we continue with the quantum sensing. As we have discussed the neutral atom, we have discussed the trapped atom, we have discussed the Rydberg atoms, we have discussed atomic clock. Now in this series we discuss now the solid state spin. Now the solid state spin, where we are having the NV center assembles as well as NMR sensors that we use. After that we discuss the solid state spin single spins, means where we discuss the semiconductor quantum dots, and we discuss the P donor in SI and the single NVP center. And we are also discuss the superconducting circuits, where we use the flux qubits and the charge qubits. After that there are the elementary particles which we use as a sensor, like muon and the neutron. Then there are the other quantum sensors also, like SET, like photonic, like opto, interferometers like opto, where we use the phonons, and in the interferometer we use the photons as well as we use the atoms and molecules. Now today we discuss the quantum sensing of electron beams using the solid state spins. Now as we know that the scattering experiments with energetic particles such as free electrons have been historically used to reveal the quantum structure of the matter. However, realizing coherent interactions between the free electron beams and the solid state quantum system has remained out of reach owing to their interstitial weak coupling. So, realizing such coherent control would open up opportunities for hybrid quantum platform by combining free electrons and the solid state qubits for coincident quantum information processing and nanoscale sensing. So, we use this solid state qubits and the free electrons interaction. The experimental observation of the coherent interactions between the modulated electrons beams and the quantum system has remained elusive. So, three primary roadblocks have impeded progresses, like first, where we use the interaction strength is inherently weak, demanding large electron beam current, near perfect punching at the modulation frequency, and a small impact parameter. Second, decoherence. First is the interaction strength, second is the decoherence. In this decoherence mechanism, due to the quantum system's interaction with its environment, may place even stricter constraints. Necessarily, we use the electron beam drive rates faster than the decoherence process. The third is the building experiment platform that integrated well controlled quantum system with electron microscopy, which is remain the technically challenging for the scientist. So, recent experimental advances include observation of free electron induced decoherence mechanism in hexagonal boron nitride color centers, as well as the integration of the spin precession sensing with the electron beam. So, there are the three main primary roadblock that we will use in the solid state spin. First is the interaction strength, second is the decoherence mechanism, third is the experimental platform that integrate the well controlled quantum system with the electron microscopy. So, as a proof of the concept step towards exploring the free electron spin interaction, spin qubits, especially the negatively charged nitrogen vacancy, that is the NV center in the diamond, could be employed as the quantum sensors to interrogate electron beam interaction. So, a prerequisite to the quantum control experiments would be to detect a signature of the modulated electron beam in the NV resonant spectrum or in its characteristic decay time. So, we use the NV centers, which are the one of the most widely used solid state spin qubit platform. That is because of their room temperature operation, and that has having the long coherent times, strong sensitive to the electric and magnetic and strain field, as well as their straightforward and readout control scheme. So, by establishing such a fingerprint would be a critical step and which is towards the control of the solid state spin qubit with the free electron, while simultaneously providing a metallurgically benchmark for a free electron qubit coupling strength under the realistic experimental condition. So, a general framework to realize quantum sensing of electron beams with solid state spin qubits. So, in this an experimental platform to probe interactions between a modulated electron beam and the spin degree of freedom of optically active solid state defect. So, in this we discuss the interaction between the modulated electron beam and solid state spin, how the solid state spin and the electron beam are interact. So, that is the interaction between them. So, in the first principle, fully quantum mechanical description of the interaction between a modulated electron beam and a solid state spin that include the realistic decoherence pathway for the spin. So, such as homogeneous and inhomogeneous transverse decoherence rate and the energy relaxation. So, an electron beam, that is the average current, that must be having the I naught focused near the impact parameter and the surface of the substrate that containing the optically active solid state spin. So, now we can have an electron beam that is having the average current, that is the I naught, and that is focused near the impact parameter, that is the P naught, the surface of the substrate containing the solid state spin. So, in this diagram we are having that there is a electron beam and there is a magnetic field generated, that is a magnetic coupling, and there is a spin polarization and the readout. So, now and we are having the basically we are having a M W's control here, which is on the qubits, and moreover there we are having a solid state spin qubits, and that does assembles and ensembles. So, the concept of schematic setup of this, we are having a modulated beam of the electron impings on the bulk crystal containing an ensemble of the solid state spin. So, the magnetic field generated by the beam couples the spin. So, the spin can be initialized and read out throughout the laser pulses and controlled by the external applied microwave derived field. So, you can see here that it is the adjusted by the microwave control, and moreover there is an there we are having that a spins and then spin having a polarization, and that can be read out. An ensemble we are having the solid state spin, and for detecting an electron beam using the solid state spin qubits, an electron beam passes through a medium, that we are having a crystal, after that creating a magnetic coupling, that is the B with an we are having the electron beam that passing through the medium, that creating a magnetic coupling, and that in the solid state spin qubit. So the qubit are controlled by the microwave pulses. So that's why exciting them from the vertical line and the zero close angle break to the vertical line 1 close to the angle state. So that is defined by the 0 and 1 state. So the interaction with the electron beam causes the qubits to relax, and which can be detected through a spin polarization and the read out process. So this method allows for the sensitive detection of the electron's beam current via the spin relaxometry. Means we can find out that is work as a sensor which is based upon the spin solid state spin that can detect the sensitive electron beam current. So that is why we use it as a solid state spin sensors. So now again we are having another diagram, then how it is working. So through this we can find out the sensing. So quantum sensing in a modulated electron beam line, where this schematic of the experimental setup consists of a bunched electron beam that is interacting with a spin system that has been theoretically defined in the some reference, and in addition a confocal microscope with the microwave control is integrated to the beam line to initialize, to control and to read out the spin state. So in this, although the introduces a direct spin decay path, and it effects can be typically be neglected for a macroscopic beam current that is considered here. So however, a much stronger resonant interaction can be engineered by modulating the electron beam current, that can be defined by IT is equal to I naught plus I resonate, that is why RES cos omega I and T. So we are having to the match with the qubit transition frequency, that is omega naught. So here we are corresponding towards the 0 to plus minus 1 transition, whose degeneracy may be lifted with a DC magnetic field. So under the rotating wave approximation, we are having the Hamiltonian that will be given by H is equal to del by 2 sigma to Z plus, because we are talking about the Z direction, plus I resonance phi 0 divided by 2E into sigma x. So these are used for the polymetrics. Sigma x, sigma z are the polymetrics, and del, which is the detuning, which is the difference between the frequency. So omega 1 minus omega naught. So in this manner we can have the rotating wave approximation. So experimental effect towards observing the free electron spin interaction, the starting by introducing the platform, and that is integrated a home built confocal microscope into a bunched electron beam line. So the beam line that consists of a thermionic electron emitter accelerated to the 10 kilo electron volt, that is aligned through the chamber with steering magnet and focused down to the focal spot, that is A is equal to 10 micrometer, with a solenoid lens on a diamond bulk sample. So which is common for the large current beam line, which is greater than mu ampere. So these can be used to detect the thermionic electron. So the beam is bunched by the gigahertz cavity, that is flowed by a, the value is 50 centimeter drift length. So realizing close to perfect bunching. So the sample can be aligned with the several transition stages in the vacuum chamber and may be reacted to measure the average current on a Faraday cup further downstream. So, to polarize and read out NV spin ensemble, then we use a combination of optical pulses that is delivered by the 520 nanometer green laser diode modulated by a orchesto optic modulator or a laser diode control. So, optical excitation is synchronized with the microwave pulses delivered by the omega shape wire deposited at the surface of the sample. So, emission from the NV assemble is collected with a single photon counted module. So, the focal point of both the optics and the electron beam can be adjusted to coincide on the sample within the omega shaped wire. So, here we are having a omega shaped wire, you can see easily, and here it is the NV chip mounted on the sample stage, and that is in between that we are having the NV assemble, and we are having the excitation with the green and the readout that is in the red light. So, from here it is detected. So, false color optical micrograph of the chip under coincident electron beam and the laser illumination. Right hand side you can see there is the false color optical micrograph of the chip under the coincidence electron beam and the laser illumination when these are interacted. So, characterize the influence of the bunching cavity on the electron beam. The cavity is thermally tuned to be resonance with the spin qubit, and that estimate the cavity generates an approximately perfectly bunched beam, and that is the cathodoluminescence imaging that reveals that the cavity modulates the beam transversely at 2 omega I. So, producing a double peak profile with the optimal bunching achieved at approximately 15 dBm and that derived power without excessive transverse spreading. So, this is the solid state spin. Now, we discuss the solid state spin single spin sensor. So, now if we talk about the readout of the single spin in the solid state, a major milestone on the road towards the quantum computers has been achieved by the both the electrical and optical scheme. So, electrical readout has been demonstrated with the phosphorus dopant in the silicon and the electrostatically defined semiconductor quantum dot. So, solid state single spin work on the electrical as well as on the optical scheme. So, in the electrical we are having the phosphorus dopant in the silicon and the electrostatically defined the semiconductor quantum dot. If we talk about the optically readout, and it was shown with a single organic molecule like optically active quantum dot. It is the optically active quantum dot, that is a single organic molecule. So, and defect centers in the crystalline material including the diamond and silicon carbide. Diamond, as we are talking about the carbon, and other materials we can also take. So, we are having the carbon as well as we are having the silicon carbide just for the single dot. So, now mechanical detection of the single parametric defect in the silica and the real time monitoring of few spin fluctuations have been demonstrated. So, that is the that we will define for the single spin, solid state single spin. So, we take the material and then we just detect the single spin. The another sensing is the superconducting circuit. In the superconducting we are having the squid. Squid we have already discussed in the previous lecture, that is simultaneously one of the oldest and one of the most sensitive type of the magnetic sensor, and that we have discussed in the one of the lecture, the working of the squid as well as how the squid work. So that we have discussed where we are having these that we discussed that these devices, interferometers of the superconducting conductors, measure the magnetic field with a sensitivity which is down to the 10 AT divided by root hertz, that has been defined. So, their sensing mechanism based upon the Arnold Bohm phase imprinted on the superconducting wave functions by the encircled magnetic field, which is read out by a suitable circuit of the phase sensitive Josephson junction. So, that we have defined. Another series we discuss the superconducting qubit, that we will discuss in the next lecture, that what is a superconducting qubit, how it work, and what are the qubits and qubits that will be used in the superconducting, that is a superconducting qubits. So, on how it is used for the sensing purposes. Thank you very much.